So we will now analyze the physical importance of the relations that we just wrote down. Okay. So remember that in the last semester we talked about orbital angular momentum. Orbital angular momentum L is, so the orbital angular momentum is constructed explicitly from X operator and P operator. So L is X cross P. Right? All of these are operators in quantum mechanics. And we used the specific representation of the orbital angular momentum to derive commutation relations between the different angular momentum components. And we also discussed that the commutator of L with Vj, as I've written in the box before, is simply epsilon ijk Vk, which means that the action of rotation mixes the components of the vector operator. Okay, so at this point we have to pause and realize that there is a lot of similarity between the J that we have discussed and the L that we have already discussed. So particularly the commutation relation between the different J components is Jk, which is exactly similar to the commutation relation between the different L components. Okay, and we also discussed that the commutator of Ji with any vector operator Vj simply mixes the components of the vector operator. And this is also true for the orbital angular momentum. Okay, so we now have to wonder if J and L are the exact same things, or is J slightly a more involved object than L? Okay, to understand. So basically, whatever I have done about J, I've started by assuming that it is coming from spatial rotations, which means that this Rij was the fundamental thing, right? Rij is the matrix that rotates in the three spatial directions, and U is the corresponding operator in the Hilbert space that is realized as an operator on the Hilbert space that rotates all the states. So fundamentally, is there any difference between J and L? Okay, so this is the question. We will answer this question in two parts. I'll give you a rough heuristic answer now, and once we develop the angular momentum Hilbert space a little more and talk about the eigenvalue problem, it will become clear that J and L are not the same objects in general. So for now, let us actually do a very simple exercise. So let us say that let me construct. So J is a linear operator that has the units of angular momentum. L is a linear operator that has the units of angular momentum. So I want to understand if I construct a difference in these two quantities, J minus L. What is this operator? Okay, if J and L are the exact same things, it should be a null operator. But let us actually investigate if this is actually a null operator. Let me actually write this as some S. Okay, in other words, I'm claiming that J can be written as L plus S. Okay, so what is this S operator, and does it have all the necessary conditions of being an angular momentum given these commutation relations that J and L have? So let us do a very simple calculation and simply plug this definition in these various examples. Okay, so first let us look at JIVJ equals Vk. And in this relation, let me assume that Ji is composed of an addition of L and S. Now remember that I have not told you exactly what this addition means. We will clarify this in the later lectures. I'll tell you exactly how to add angular momentum. But for now, simply assume that such an addition exists, and I can define J as an addition of L and S. Or in other words, I can define the difference between J and L and call this new operator S, whatever this new operator is. So substituting Ji equals Li plus Si in this equation, I have Li plus Si Vj equals sorry, instead of vi, let me actually take a specific vector example. Since this is true for all vector operators vj, it should also be true for the orbital angular momentum operator lj. So let us take vj, excuse me, let us take vj to be the orbital angular momentum itself, in which case ji lj should be equal to I h bar ijk vk now becomes lk. Okay. Now again, if s is equal to 0, this is simply the relation li lj is epsilon ijk lk, which you already know. So no harm done. So let us investigate if what happens if ji is si plus lj. Well, if ji is si plus li, then I can write this as li plus si comma lj commutator is this guy. Okay, which means I can split this into two commutators, LILJ plus SILJ equals LK. Okay, but you know already that the commutator of Li with Lj is precisely IH bar epsilon ijk LK. So you can realize, you can easily see that this actually cancels this cleanly, which tells you that the commutator, whatever you define as your S operator, it has to commute with the orbital angular momentum. If this is a non-null operator, then this operator should be such that it commutes with all the generators of orbital angular momentum. Okay. This is the first point, which means that I can measure orbital angular momentum and measure spin exactly at the same time independently, because they have nothing to do with each other. Okay, they can be precisely measured simultaneously. That is the first point. The second point, yes.
Here you write the commutation relation of between ji and lj equal to I squared epsilon ijk lk. So why did you write lk instead of ji minus j?
What did I write? So remember that if the commutator of j, oops, excuse me, the commutator of ji with any vector operator vj follows this relation, right?
Yes, sir.
So as a special case of a vector operator, I took orbital angular momentum.
But what about the commutation relation of Li with any vector?
You can use that one also, but
Why?
I'm talking about j as an addition of l and s. So if you want to do it that way, you can take li vj and write this as I epsilon ijk vk, right?
Yes, sir.
Okay, and now I can write li as the difference between ji and si, right?
Yes, sir.
Agreed?
Yes, sir.
Now again, I can split this into two commutators, ji vj minus si vj equals IH bar epsilon ijk vk, right?
Hmm.
But I know that JIVJ commutator is also I epsilon ijk vk, so this cancels this part, which tells me that the commutator of SI and VJ is equal to 0.
Okay. But the thing is that commutation of Li and Vj equal to I squared epsilon ijk Vk. If I substitute Vj with Lj, then isn't the right hand side should be substituted by
Sorry,
Vj?
can you say that again, please?
Here you are substituting uh, when you are using the commutation relation of Li and Vj. Okay. If
Li,
I yeah, Vj equal to I squared epsilon ijk Vk. Okay. If I substitute Vj with j j jj, okay, then in the right hand side shouldn't be the jk I squared epsilon ijk jk.
correct, absolutely.
That is why I'm confused, because where in that portion you use the lk.
Huh, but you can use this one also similarly and get the exact same conclusion. All I'm trying to get at is that SI. See, remember, all we are trying to understand is if L and J are the exact same things or different things. Does it make sense to introduce an S or not? That is all.
Okay. Yes, sir. It makes
How you
sense.
get to it is completely up to you.
Okay, sir.
So if so, let's actually follow that line of thought. See if it gives us ijk jk right? Now I substitute J is equal to L plus S here. So Li Sj plus Li Lj, agreed? Equals IH bar epsilon Ijk Lk plus Sk, agreed?
Yes, sir.
So now you're saying that this would cancel this and the commutator would be non-zero. Okay, I'll come back to this question. It's a good question.
Okay, sir.
Okay. So we find that the components of S and the components of L commute. So this is the first relation we get by simply assuming that there is an S operator that can be defined as a difference between J and L operators. Excuse me. Now, go ahead and use it in the first relation. Jij is, I think this is what you also said. Jij is IH JK. Okay. And then I will write this as Li, excuse me, Li plus Si, comma, Lj plus Sj equals IH bar epsilon Ijk Lk plus Sk. Okay. So if you piece up this commutator, you get four different parts. The first part is Li Lj. The second part is Li Sj. The third part is Si Lj. And the fourth part is Si Sj. On the right hand side, you have two terms. Okay. Now, from the previous discussion, we know that the components of L and S commute. So this is equal to 0 and this is equal to 0. Okay. And we also know that this exactly cancels this because that is exactly the commutation relation of Li and Lj, which leads us to the relation that the commutator of the components of S transform exactly like the components of L or J. So it makes sense to call this an angular momentum because the components transform. Well, this doesn't exactly rationalize it, but at least the components of S transform in exactly the same way as the components of L or J, which has the exact same commutation relations as S or J. Okay. So now the question is, how do we construct this S operator? And this is a more difficult question. And we will have to come to this slowly, the answer to this slowly, but we can actually talk about how not to construct this S operator, at least a glimpse about how not to construct this S operator. Well, the L operator we know is constructed out of position and momentum, right, as X cross P. So the question is, can the S operator be also constructed out of position and momentum? And the answer is no, it cannot be constructed out of position and momentum because we know that the commutator of S and L is 0. So if S is composed of position and momenta, then we have to have a operator such that since L is composed of position and momenta, we cannot in general have the commutator of two functions of position and momenta to be equal to 0 because position and momentum do not commute. Okay. So that is one way to look at it. The other way to formalize it is by taking this relation. So Si, oops, wrong color. So Si Lj equals 0, right? Now I know that L, Li, Vj for any vector operator is IH bar epsilon Ijk Vk. And let me specialize this to the position operator or momentum operator, it doesn't matter which one. So Li Xj equals IH bar epsilon Ijk Xk. Okay, you also know that Li Pj is IH bar epsilon Ijk Pk. They are both vector operators. So this is the commutation relation between the two. And J also behaves exactly the same way as L. So you know that Ji Xj would also mix the components of the position operator. Okay. So now take this and form the difference between these two commutation relations. Or a simpler way to do this would be to take this relation and substitute this as Li plus Si comma Xj. Okay, Xk. Which tells you, since Li with Xj is Xk, this tells you that the commutator of Xi with the position components is also equal to 0. And similarly, you can also show that the the commutator of Si with the momentum operator is also equal to 0. Which means Si cannot be constructed simply out of position and momentum operators, because you have to satisfy both these relations. Okay, and in general, any if Si is a function of momentum, Si comma Xj will not be equal to 0, and if Si is a function of position, Si comma Pj will not be equal to 0. So Si cannot be constructed out of some simple combinations of X and P. So at least this gives you a glimpse of how not to construct S. But to understand how to construct S, we have to do a little bit more work, which we'll come to in a second. So what have we done in this short section? What we have basically done is to say that the definition of J, even though J, the angular momentum commutation relations for J and everything else seems very similar to L, there is a crucial difference between the way we constructed the commutation relation for J and the way we constructed the commutation relation for L. In the case of J, I did not presume any form for J, right? So the commutation relations fell from very general considerations about how spatial rotations should be realized in the Hilbert space. But the commutator of Li, Lj, we can actually derive by claiming that L is X cross P. In fact, this is how we derived it last semester. If you substitute Li equals, so if you substitute Li, since L is X cross P, so excuse me, since L is X cross P, we can take any one of the components. This is equal to epsilon ijk xj pk, right? And then explicitly calculate Li Lj using this definition, and that is what you would get, whatever that is. So to calculate the commutation relations between the L components is very straightforward. Because we have a form for L explicitly. But to calculate the commutation relation between the J operator, J components, we did not take recourse to a particular form for J. We simply did it from very general considerations as to how a infinitesimal rotation operator should look like in the Hilbert space. So it invites us to question whether J can be equal to L, or is J a little bit more general than L. And it turns out that if I add to J an L plus some other operator, which has the units of angular momentum to be consistent, it turns out that such a definition is actually consistent with all the commutation relations, provided that the new vector operator that I introduced, S, commutes with the orbital angular momentum components and has a commutation relation SI Sj is epsilon ijk sk with its own components, just like the L and the J operators do. Okay, so with this definition, the redefinition J equals L plus S is a completely consistent relation that does not violate any of the derivations that we have done thus far. And the question is, of course, I've just introduced a plausibility argument that there could be a difference between J and L. I have not actually shown that there is a difference between J and L. To understand that there is a difference between J and L, we have to do the eigenvalue problem, which we will do next. But this is a plausibility argument to show that the difference between J and L doesn't automatically have to be equal to 0. It could be 0, it could also be non-zero. Okay. To investigate what this S operator is, we will now turn to a more rigorous calculation of trying to understand the eigenvalue problem of J square and J3, just like we did the calculation for L square and L3 in the last semester. So before I move on to that particular problem, do you have any questions about any of this?
Sir?
Yes.
Sir, here is follow the same commutation relation as J and L. Okay. So from that, can I say that S has some fundamental nature that is related to the L and S? No, L and J. Some
Yes,
fundamental. Yeah.
yes, absolutely. S is a very, very fundamental object, as you would see. In fact, you can also argue that it is, in some sense, more fundamental than L. But yes, it is certainly a very fundamental object, and all elementary particles have a specific value of S.
And so there's also another question, sir. Here you use the commutation relation of S and L, and you said that as they are commutating with each other, you said that S can't have P and momentum and the position operator constructed out. But the thing is that if I find some operator that commutation relation with Li is not equal to 0, then can I say that that operator is constructed out of position and momentum only?
So the question is, if you find some operator that commutes with Lj, then
Yes, sir.
so no, the reverse argument doesn't usually work. So see, you can always come back and say, look, yes, I can always construct a very special operator that maybe commutes with X and all components of X and all components of P, uh, but it is still constructed out of X and P, right? Your question is basically saying that, right?
Yes, sir. Yes, sir.
Um, Perhaps, but this is not how it works. So
Okay, sir.
I do not know of a way of constructing an operator, any linear operator. So it should also be a linear operator. Yeah. If you construct any linear operator, it will be very hard for me to see how you can construct something out of X and P that commutes with both X and P.
Oh,
I don't
okay,
know.
sir.
Take it as an exercise and see if you can do
Okay, sir.
it. Okay. So we will move on now to the eigenvalue problem of J square and Jz. Sorry, J3. So why J square and J3? Oh, again, my thing is, sorry. Okay. So some days Bluetooth misbehaves much more than the others. Okay. So what does this mean? Let me actually set up the problem first. So we want to understand the nature of the Hilbert space. So what does that question even mean? So first, let us look at the J square operator. J square operator is a scalar operator, which is J square. You can write it as Ji. Okay. Now you can ask the question, how does J square transform under rotations? And you can easily show that J square does not transform under rotations. In other words, if I sandwich J square between U dagger and U, which is how operators transform Ji, you would actually find Ji. Okay, this is an exercise for you. Please show that this is equal to true. To show that this is equal to true, you have to use the fact that the R operator is an orthogonal matrix. So U dagger R Ji. Since U is a unitary operator, I can sandwich a U dagger here and U. Okay. Now you know how the J components transform. The J components, and this is equal to the J components transform as mixing. So the rotation basically mixes the J components together. So this can be written as Rij Jk, and this can be written as Ril Jl, and then you can use the orthogonality of R matrices to show that the J square operator is a scalar operator that does not transform under rotations. This is a roundabout quantum mechanical way of stating the simple fact that the length of the vector doesn't change under rotations. Okay, J square is a length. It's a scalar operator. So if you have troubles with this, we can visit this in a tutorial problem. Okay. So J square is invariant under rotations, which means J square commutes with Ji. Okay, either J1, J2, or J3, all of them. It commutes with all different components. But notice that the different components of Ji do not commute with each other. In fact, Ji, Jj is IH bar, epsilon, IJK, JK, which means if I want to understand how these operators look like, for example, in the matrix form or whatever it is, I can go ahead and diagonalize these operators, and I can diagonalize simultaneously the J square operator and one of the three J operators. Okay, but I cannot diagonalize all of them simultaneously because the Ji's do not commute with each other. So conventionally, this is taken as J3. So our goal is to understand how to diagonalize J square and J3 simultaneously. Okay. So let us assume that J square and J3 have, so this is now clear, right? Because J square and J3 commute. And since the other components of J do not commute with J3, I cannot simultaneously diagonalize all the operators. Then that will make the problem really easy, but unfortunately it is not that easy. But I can diagonalize J square and one of the three J matrices simultaneously, and this is conventionally chosen as J3 or Jz, depending on which book you're looking at. Excuse me. So let us assume that there is a simultaneous set of eigenvectors for J square and J3. And let me call these eigenvectors, let me label these eigenvectors following Shankar's notation. Let me label them by the eigenvalues of J square and J3. So let me say that J square acting on alpha beta, this is the simultaneous eigenket, is alpha times alpha beta, and J3 acting on alpha beta is beta times alpha beta. Okay, the ket alpha beta should be understood as alpha comma beta. It is a ket that is labeled by the eigenvalue of J square and eigenvalue of J3. Okay. Now, what do I know and what do I not know? I don't know alpha. I don't know beta. I don't know the eigenkets alpha beta. All I know are these two commutation relations. Okay. And remarkably, they will prove to be sufficient to understand everything else. Now, it is not enough if I understand the action of J square and J3 on alpha beta. I also have to understand how J1 acts on alpha beta. Okay. Now, obviously, J1 acting on alpha beta and J2 acting on alpha beta would be more non-trivial because since J1 and J2 do not commute with J3, J1 and J2 matrices will not be diagonal in this basis. So this will not be equal to something times alpha beta, right? So it will be something more complicated. So we'll have to understand how J1 acts on this in this Hilbert space and how J2 acts on this Hilbert space. Okay. So let us expand the number of questions we do not know the answers to. We do not know what is the ket alpha beta. We do not know the eigenvalue alpha. We do not know the eigenvalue beta. We do not know how J1 acts on these kets alpha beta. We do not know how J2 acts on these kets alpha beta. So we are starting with a clean slate. We do not know anything. All we know are the two commutation relations. Okay, this is our starting point. Any questions about this? This is the setup of the problem. I need to figure out the eigenkets alpha beta. Once I figure out the eigenkets alpha beta, everything else should be hopefully smooth. Excuse me. Okay. Now, let us start by writing down, instead of working with J1 and J2, it turns out to be more fruitful to work with some linear combinations of J. So let me define two operators, J plus minus. This is equal to J1 plus minus IJ2. Okay. So J plus is J1 plus IJ2 and J minus is J1 minus IJ2. Excuse me. Okay. So instead of asking about how J1 and J2 act on alpha beta, I can equally well ask about how J plus and J minus act on the kets alpha beta, because I know that J1, this implies that J1 is simply 1/2 j plus plus j minus, and j2 would be 1 over 2i times j plus minus j minus, right? So if I know how j plus and j minus act on these skets, I know how j1 and j2 acts on these skets. So I can as well stick to j plus and j minus. I can always define linear combinations of linear operators and work with them instead of the original operators. Nothing prevents me from doing so. Okay. So alpha, beta are simultaneous eigenkets of j square and j3. We need to understand the action of j plus and j minus on these skets. Okay, this is our problem. First, let us reformulate the commutation relations with respect to j plus and j minus. So let us calculate j3 comma j plus. Or rather j plus j3, it's all the same thing, it doesn't matter. What is j plus j3? This is equal to j1 plus ij2 comma j3. So this is equal to j1 comma j3 plus I times j2 comma j3, right? Now the commutator of j1 j3 is minus j2, and the commutator of j2 j3 is plus I j1. Right, it is a cyclic commutator. The commutator of 1 2 is 3, 2 3 is 1, and 3 1 is 2. So the commutator of 1 3 is minus 2, which means j plus j3 commutator is equal to oh sorry, I forgot an h bar here somewhere, right? So the whole thing is multiplied by an h bar. So this is equal to, if I pull out the I, so I can write this as h bar times ij1 plus I square j2. So this is equal to ih bar times j1 plus ij2, which is ih bar j plus. Is this right? No, this is not quite right. I'm sorry. So let me do this again. There is 2 factors of I that I missed. Okay. So let me do this carefully. So this is j1 comma j3 plus I times j2 comma j3, and j1 comma j3 is minus ih bar j2 plus I into j2 comma j3 is ih bar j1. So if you do this right, you would get minus h bar j1 minus ih bar j2. Okay, so which means if I pull out the minus ih bar, I get j plus. So the commutator of, if I make the left hand side also ulta, the commutator of j3 and j plus is plus h bar j plus. Okay. Similarly, you can show that the commutator of j3 and j minus is minus h bar j minus. Excuse me. Okay. So let us write down these commutation relations again, because this will turn out to be very fundamental in how we are looking at the problem. So instead of working with J1 and J2, we are working with J plus and J minus. And we have, instead of working with the commutator of J1 with J3 and J2 with J3, we are working with commutator of J3 and J plus and J3 and J minus. Okay. All right. So now obviously J square commutes with all components of j plus and j minus, because j square commutes with all components of j square commutes with j1 and j2, obviously. So this is obviously equal to 0. So we are left with these three commutation relations that we have to exploit to solve this problem. Okay, is this clear? Are there any questions about this? Okay, so we will briefly discuss the importance of one of these commutation relations, and then we will stop. It will give us a hint of how the problem is going to proceed. So let us take the relation j3j plus equals h bar j plus. Okay, now remember that one of the questions that we asked was, look, suppose if you are successful in diagonalizing j square and j3, okay, you know what alpha is, you know what beta is, and you know the eigenvectors alpha beta. How do j1 and j2 act on these eigenkits? Well, I cannot, if I don't know the eigenkits, I cannot directly answer how j plus or j minus act on these eigenkits, but I can get a hint of how the relation proceeds, because I know that j3 alpha beta is the eigenvalue is beta. Okay, so now this is an operator relation. So let me act both sides of this operator relation on the kit alpha beta. So j3 j plus acting on alpha beta equals h bar j plus alpha beta. Remember that I do not know what j plus acting on alpha beta is. I do not know what the right hand side of this equation is, but this equation still tells me something very important. So to understand what this is, expand the left hand side. So this is j3 j plus acting on alpha beta minus j plus j3 acting on alpha beta equals h bar j plus acting on alpha beta. Okay. Now j3 acting on alpha beta is just beta times alpha beta. So I can write this further as j3 minus beta j plus alpha beta equals h bar j plus alpha beta. Now j plus acting on alpha beta is some ket. I do not know what that ket is. So let me write this more suggestively as j3 acting on the ket j plus alpha beta. And this can be written on the right hand side as beta plus h bar j plus alpha beta. Okay, and this is the crucial point. I do not know what this ket j plus acting on alpha beta is, but I know that whatever this ket is, it is an eigenket of j3 with an eigenvalue beta plus h bar. So this tells me that whatever this ket is, j plus acting on alpha beta is an eigenket of j3 with eigenvalue beta plus h bar. Okay, but I know the eigenkets of j3. Eigenket of j3 with eigenvalue beta plus h bar, but I know that the eigenket of j3 with eigenvalue beta plus h bar is just alpha beta plus h bar. So whatever this ket is, this j plus alpha beta, it cannot be anything random, because it is already an eigenket of j3 with eigenvalue beta plus h bar, which means this j plus acting on alpha beta, well, it doesn't have to be exactly equal to alpha beta plus h bar, because it can be related to alpha beta plus h bar with a multiplicative constant. So I will write this as some c plus, which is a function of alpha beta times alpha beta plus h bar. Okay, so this tells me that this Hilbert space is such that I can keep going up in the eigenvalue of the j3 operator in units of h bar, because if I apply j plus square on alpha beta, obviously I'm going to get alpha beta plus 2h bar. If I apply j plus cubed on alpha beta, I'm going to get alpha beta plus 3h bar. So whatever this Hilbert space is, it is reminiscent of our harmonic oscillator problem, where we went up a ladder by applying the raising operator. The raising operator in this case is a J plus, which raises, so the J plus operator raises the eigenvalue of J3 in units of H bar. Okay. So it raises the eigenvalue from beta to beta plus 1 H bar, a beta plus 2 H bar, and so on and so forth. Okay. Similarly, we can show that the J minus operator lowers the eigenvalue of the J3 operator by, again, units of H bar. So how we use these two pieces of information to understand this Hilbert space further, we will take it up at the next lecture. Today we will stop here. But please understand that we are starting with nothing but the assumption, nothing but the statement of commutation relations, that J square commutes with Ji and Ji and Jj do not commute with each other. Using just these two pieces of information, we will try to get as much information as possible about the eigenvalue problem of J square and J3. We will continue this in the next lecture. Okay. So let me stop the recording, and you can ask if you have any questions.